So we are playing with limits of a function. And normally, for most functions in most places, limits are a pretty straightforward thing, but every once in a while, there are some trouble. And so first, we'll just go over the straightforward part. So we have some function, f of x. You can graph that function. Maybe that's our function right there, some kind of polynomial function. And for most places, like if we pick some x value, let's call that a, we plug it into the function and we get this y value. So we get a y value, it's a y right there, called f of a. We started with an x value called a, right? And we have this point right there. And the idea that the limit as x approaches a of f of x is often just the function value. This property right here is an idea called continuity that we'll talk about in the next section. And it's just that limits are nice, mostly. But every once in a while, limits aren't nice. So just an actual nice limit, if we take a look at f of x equals, very simply say, x squared, and we let x equal 2. If we were to look at the graph near x equals 2, then we would find that y is going to be near 4 when we zoom in on that spot. Right? It looks nice as we zoom in. And again, so most functions, they're just nice like that. And again, the idea of limit is the idea of approaching and so we're not just looking at the point, we're looking near the point and we're kind of zooming in to see what goes on there to make sure things behave nice. So that's the idea of a limit in mathematics. And again, mostly they're nice, but every once in a while they're not nice. So when are they not nice? Limits are not nice in common places. Certain rational functions have not nice places. And we looked at a couple of examples of that last week. We'll look at a bunch more today. Other places limits are not necessarily nice are when infinity is involved. Certain trigonometric functions have some not nice places. And as you dig deeper into mathematics, you find a whole lot of places where the idea of a limit is pretty important that we just can't, we don't have this niceness of things look good near a point. So examples of rational functions that were trouble, we had looked at something like x squared minus 4 over x minus 4, or excuse me, x minus 2. And we know a lot about functions and their domains, and we know that because there's an x minus 2 in the denominator, we can't let x be 2, otherwise we get a 0 in the denominator, and that's a problem. So that's the place where rational functions are not nice, 0 in denominator. Now this particular expression takes it a whole step further. Not only if I plug in 2, do I get a 0 on the bottom, but I also get a 0 in the top. I get a 0 over 0. And 0 over 0 is what we call an indeterminate form in mathematics. And indeterminate is different than undefined. They are not the same thing. Undefined means there is definitely no answer, but sometimes there is an answer. So let's look at a graph of this one and see why. Desmos has been our friend lately. And function notation in Desmos can be your friend once you get used to it. So this looks like a nice straight line, even though it had a complicated expression here. And it looks like at 2, it looks like I have the point 2, 4 right there. But if I ask the function what it thinks about x equals 2, it's going to say, I cannot compute. That is undefined. Now, because there's a 0 in the denominator, the program's just saying undefined, but really it's a slightly different mathematical idea called indeterminate. I'm going to try to explain the difference between those right now to the best of my ability. So undefined, which is also called does not exist. So sometimes instead we say does not exist in mathematics. That's something like 2 divided by 0. What does 2 divided by 0 equal? Question mark. If we think of a different problem, like maybe 6 divided by 2, well, we know 2 goes into 6 3 times. Why do we know that? Because we know that 2 times 3 equals 6. And if we investigate this division with the related multiplication, that would mean 0 times what is equal to 2? Well, that's not possible because 0 times anything is 0. This is not possible. Since 0 times anything is supposed to be 0. It can't possibly be 2, so that's why this is undefined. It doesn't exist as a mathematical value. Now, switch over to the idea of indeterminate, which is a related but different idea. So 0 over 0 is what we call indeterminate. And if we use the same logic that division exists because multiplication exists, I'm going to put a slash in the 0 on the denominator to distinguish it from the 0 on the top for a moment. And if I say 0 divided by 0 equals what, that relates to a mathematical expression where I multiply the denominator by the quotient on the other side. And this says what times 0 equals 0. Well, take your pick. 0 times 0 equals 0. So 0 is a possible answer here. And that makes sense because I know 0 divided by 2 is 0, and 0 divided by pi is 0, and 0 divided by just about any number I want is 0. On the other hand, I was taught that a number divided by itself should be 1. Right? So I think the answer could be 1. Could 0 divided by 0 be 1? And if we look at the multiplication idea, the denominator 0 times the quotient on the other side, is this statement true? The answer is yeah, that's true too. So this works, that works. However, some days 0 divided by 0, let's use a different color, 0 divided by 0, sometimes it's 4. Why? Because 0 times 4 is still 0. So this 0 over 0 has infinitely many possible answers, and we have no good way to pick one over the other. This one seemed like a good rule here, because I have some examples of it there. This one seems like a good rule here because I know a number divided by itself is 1. It doesn't matter what that number is. Which is better, this rule or that rule? I don't know. They're both good rules. In the case of this problem I was working on right there, 0 over 0, according to the graph, it looks like it should be 4 when x is 2. So 2 forces this to be 0 over 0, but the graph shows it should be 4. And if we take that a step further algebraically, oops, wrong button, x squared minus 4 factors as x minus 2 times x plus 2. And that factor of x minus 2 in the bottom cancels because here I have a number divided by itself, and a number divided by itself is 1. Now that's going to be 1 as long as x is not 2. So that this expression here in red is the same thing as the expression x plus 2. And this function and this function will agree everywhere except where x is equal to 2. And the disagreement there is that the rational form of this function does not have a value here. It's undefined right there. But if I rename this function g of x and say it could also be x plus 2, then the green function sits on top of the red function, and the only exception is the green function does not have a hole at 2, 4. Let's see, can I actually get there? Come on, close enough. There we go, 2, 4. The green function exists at 2, 4. The red function does not. It has a hole there. So that's the idea of a limit. So a few things can happen with limits. Oops, wrong button. Let's try that again. Hello, people. So often limits are just nice. Like x squared near 2, the limit's 4. Pretty nice. This one is not so nice because it doesn't actually exist there. So some examples again. The limit as x goes to 2 of x squared is simply 4. It's just nice. However, the limit as x approaches 2 of x squared minus 4 divided by x minus 2, that happens to equal 4, but it's not so nice because there's a hole in the function, right? We can't actually plug in 2 and get an answer here. If we plug in 2, we get 0 over 0. We have to do some trickery to figure out that the result was 4 there. So this one was not as nice. But the limit existed, right? So often with functions, a limit exists. It's a number we can find. So that is, we find a number. A limit doesn't exist if we can't find a number. So a limit either exists or it doesn't. Pretty straightforward in that regard. Sometimes finding the value it exists at can be really tricky, naming that value, using some algebra, but often we can just numerically get closer and closer, right? We've done this with tables. We let x get close to 2 from the left and from the right. So that number that exists, remember these here are two-sided limits. Which consist of two one-sided limits, and we'll come back to those in a moment. When can a number not exist? So some examples of that. If we look at the function, say f of x is equal to 1 over x, and we try to look at what happens as x approaches 0 of 1 over x. Now, x could be positive or negative, so this is actually two different limits. That right there is the limit as x goes to 0 from the left side of f of x. So we're only using negative numbers, or we could take the limit as x approaches 0 on the right side. So we only use positive small values there. And what we're going to find here, two different things happened, and neither one actually exist as a number. So let's look at the graph of that. Clear, 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 new function, f of x equals 1 over x. And as x goes to 0 here, as we pick smaller and smaller numbers, the y value gets bigger. So if we plug in 1, we get 1. If we plug in a half, we get 2. If we plug in a quarter, we get 4. If we plug in a tenth, we would get 10, and so on. But on the other side, instead of the numbers increasing, the numbers are decreasing forever on the other side. We have this idea of an asymptote. So that's one way a limit won't exist if an asymptote is involved vertically. So for this function on one side, this limit does not exist. It is not a number. But often we're going to be more specific than that because the limit doesn't exist in a special way. On the left side here, these values decrease forever. And the idea of decreasing forever, we often call that negative infinity. Now with this other one down here, when we plug in positive numbers that are small, getting closer to zero, we find the y values increase. Now, again, it never hits a particular number. As we go closer and closer to zero, it keeps climbing and climbing. So this limit does not exist also, but more specifically, it doesn't exist because it increases forever. And our shortcut for saying increases forever is just positive infinity. So sometimes we will have a function where we say, hey, the limit is infinity. Now, infinity really isn't a limit though, is it? Limit means we stop somewhere, we get to a point. Infinity isn't a point, it's a direction. So very important, infinity is a direction, not a value. So infinity is a more specific way of saying a limit doesn't exist. Negative infinity is a specific way to say the limit doesn't exist. Now, since one increases forever and the other decreases forever, then we can't say plus or minus infinity for this one right here. This two-sided limit just simply does not exist. So that's one way a limit cannot exist. Now, sometimes though, limits do exist even when infinity is involved. So for example, let's take this a different way. Let's let x get big forever. For this function 1 over x. The bigger x gets, well, we have a 1 in the top and a bigger denominator. That means this whole thing is going to get smaller. Now, x is getting bigger forever, so it's always positive. And so that means we have a smaller and smaller positive value. And when we look at the graph of this sucker, we can see that as our x value increases, the y value drops down. But since we're always picking positive values, this thing is always going to be above the x-axis. So the limit of what this function can do as we move out to the right, it can't go below the x-axis. The x-axis is the line, y equals 0. So y equals 0 forms the limit of this function as x increases forever. And this is an important distinction, the idea of a limit. A limit is about approaching, but not necessarily touching. So my claim is that the limit as x increases forever of 1 over x, that limit is 0. Do we ever get to 0? We never get the touch 0. We just get closer and closer and closer. So you tell me how close to 0 to get, I'll tell you how far out to pick an x value. And I can get you that close. You tell me to get closer, I'll tell you how much farther to look out to get closer. Right. So again, a limit is about approaching, but not necessarily touching. So limit, approach, but not necessarily touch. The idea of a limit. Okay. Now, whenever we have infinity involved in a limit, or often when we have infinity involved in a limit, we have asymptotes. So this example right here, where x is increasing forever, but the y value is approaching a specific number, that's what we call a horizontal asymptote. The flip situation we looked at just a moment ago, when we had x approaching a fixed number, so the limit as x went to 0 for 1 over x. And if we go on the positive side there, then we get to say it increases forever. A situation where we flip where the infinity is, x approaches a fixed number, y approaches positive or negative infinity, that would be a vertical asymptote. Asymptote, there we go. And in both of these situations, it's about approaching, but we can't actually touch. X cannot touch 0 because then this becomes undefined. Y cannot touch 0 because then this situation is undefined. So it's an approach, it's not a touch. We can just get as close as we ever want. We just don't get the touch. So horizontal and vertical asymptotes are an important part of this idea of a limit, which you looked at this already in a previous class. Other way limits cannot exist is because they just won't settle down. So a couple of examples, the limit as x increases forever for, say, the sine of x. We know that the sine of x starts off at the origin and then oscillates. And it just goes up and down forever and ever and ever. And it does so between y equals 1 and y equals -1. And it depends on which number you pick for x. Sometimes you're closer to 1, sometimes -1. So this limit right here does not exist because it doesn't settle down. So that's a different way of not existing, right? But the bottom line, a limit doesn't exist if you can't name a specific number. So I can't name a specific number if it won't settle down. And I can't name a specific number if infinity is involved sometimes. Another example, limit as x goes to 0 of the sine of 1 over x. And this one is worth graphing because this one's a crazy one. What does that do? Turns out it's a kind of a flip of the situation above. Oops, put that in the wrong spot, but that's okay. So in this case, what's going to happen is it turns out it oscillates more rapidly as you zoom into the origin here. Oops, wrong way. And I'm just going to use the monkey wrench to change this. So if I just zoom in like from, say, 0.5, -0.5 to -0.5. And the more I zoom in, it's just going to keep oscillating more and more. It's just never going to settle down. So if we go to 0.1 on each side of 0, it just keeps oscillating faster and faster inside there, right? You can see that the rate of oscillation is increasing as we move in toward the origin here. So as x gets close to 0, this just keeps oscillating faster and faster. The closer you get to 0, the more waves there are per unit that you zoom in on there. And it just gets crazier and crazier as you zoom in. So this one right here is another example of limit does not exist because the function can't settle down as we make that approach. Does not exist. Okay, so bottom line, for a limit to exist, you have to be able to identify a number. Right? It has to be a number. Otherwise, the limit does not exist, and there are several ways a limit cannot exist. It could increase forever, it could decrease forever, or it could just not settle down. Okay. The other option is the left side and the right side just don't agree with each other, which kind of sort of happened here. So that's an overview of limits. Let's do some specific problems.